Okay. Good evening, everyone. So today we'll continue with the biochemical conversion. So yesterday, can someone just quickly summarize what we have seen yesterday? Anyone just summarize whatever we have seen so far in this?
Sir, so yesterday we talked
Yeah.
about, you explained about biodigestion, biomethanation, the different
Yeah.
phases of biomethanation,
Mm-hmm.
and about the factors which affect the production of biogas.
Right. What are those factors?
Uh, One is pH,
Mm.
then the temperature, the
Yeah.
solid content, which has to
Yes.
be at around 8-10%,
Yes.
loading rate,
Yeah.
and seeding, like just like how
Yeah.
we put curd to milk, similar thing.
Mm-hmm. Yeah. Yeah.
And uniform feeding. And uniform feeding is basically we can have two types, like either have a uniform feeding or in batches,
Yeah.
right?
So that is different. That is continuous and batch type. Yeah, but you're basically
Okay,
right. Mm.
okay. And then the carbon to nitrogen ratio,
Yeah. How much should that be maintained at?
30:1.
Yeah. And why is that? Why should it be maintained at 30:1?
Um, don't know, sir.
Like,
Okay,
because
maybe.
the microorganisms consume 30 times, I mean, the carbon 30 times faster than the nitrogen.
Okay,
Okay. So the
yes,
carbon kind of, gets over quickly than the nitrogen. So you need to supply more carbon than nitrogen.
yes, sir.
And what is the use of nitrogen for the microorganisms? So both carbon and nitrogen, what are they used for?
Carbon is used to produce methane.
I mean, that is for us, right? I mean, what does the organism care whether it's producing methane or ethanol?
Okay,
Why nitrogen is used for to make nucleic acids.
Sorry?
Nitrogen might be used to make nucleic acids for it to
You
divide.
can you repeat? I mean, I'm not able to. It's not
nucleic
very clear.
acids.
The nitrogen might be used to make nucleic acids for it to divide.
Okay, like it's protein basically for the microorganisms.
Yeah.
Okay,
Nitrogen is basically protein. So using protein, you build your own you know tissues, cells and tissues. It's important for that. Okay. And what is carbon used for?
carbon is for its structure.
No, that is nitrogen,
No,
right?
that is nitrogen. Yeah,
Carbon can also be used for
carbon
the
is
structure
it's
because,
yeah.
yeah, structure because everything that we see around us is carbon based. But then nitrogen is more important for, for its structure. So carbon is used for energy, like just to run its
Yes,
day-to-day activities, basically. Okay.
yes.
So yeah, so these are the factors affecting the biogas production. And then we also saw the classification of biogas plants, right? So it can be classified based on, and we stopped right here. Like, so the classification of biogas plants, you have continuous type and you have batch type. The continuous type, you have a continuous input and output. Okay. And every day you'll get almost the same input and output. Batch type is where the process is happening for days on end. So you have one input and then one output. That's it. And then you clean the tank, you clean the biodigester, and then you repeat this process. So maybe you have it for 40 or 50 days. So at the end of 50 days, you take out the gas, you take out the sludge, and you clean the tank, and then you put the biomass in again. Okay. And then based on design, you have floating drum type and fixed dome type. floating drum type is as the gas is formed, the gas moves upwards, right? So there is a drum on top of it, which is inverted and placed on top of the biodigester. So the drum also moves up because of the pressure exerted by the gas. So in the fixed dome type, what happens? The pressure just keeps increasing. There is no space to go. The volume remains constant. Okay. So that's the basic difference between these two types. And yeah, so now we'll see the different types of different biodigesters installed in India and elsewhere. Okay, so we spoke about the single stage and dual stage. So why single stage? What happens is you have the entire process happening in one reactor. Okay, and here you have the digesting slurry and supernatant layer. What is supernatant layer? So if you have, let's say you have a solution, or if you have a colloid or something. Okay, let's take a suspension for example. Okay, so when you mix it, okay, there is a lot of turbidity and all the impurities within the water is like moving around. You keep it for a while, okay, without mixing it. What happens is all the dust and everything, the suspended solids, they all settle down. And on top, you have a clear uh, kind of water, right? Clear liquid that you can see. That is supernatant layer. So one example is if you have seen buttermilk, right? You add water to curd and then you try kind of mix it. You keep it for a while. All the curd settles down and then you have a layer of water on top. So that liquid or translucent liquid is supernatant layer. Scum layer is if there are some organic materials that don't actually mix properly, they don't go into the bottom of the reactor, they float on top and they are not actually digested. They inhibit the digestion process, in fact. Okay. So the scum layer either so it can be prevented by either mixing properly or it has to be removed time and again. Okay. So within a single reactor, all of this happens. So there is digested sludge also, which has to be removed. But what is the issue with the single stage digester? There is one major issue is, as I said, the first most important thing, most important factor is the pH. The pH has to be maintained at around 6.5 to 7.5, so in the neutral range. But what happens is in the second phase where acids are formed, the pH drops, although it is organic acid. So pH doesn't drop too much, it still drops. Okay. And the acid forming bacteria multiply more quickly than the methane forming bacteria. So if the methanogenesis takes place quickly, then the acid is consumed and the pH is maintained. Okay, the pH increases again. But then if like I said, the population of the acid forming bacteria is more and more acid is produced, that is kind of toxic for the methanogenic bacteria, or it is more like the reaction does not move forward at the pace that we require it to. Okay, so that's what happens, and that is the main drawback of this kind of reactor or biodigester. So to overcome this, we have like a two-stage biodigester. The first stage is you have the acid formation happening in the first stage, and you can see a mixer here. There is a stirrer, okay, and that is done to avoid the supernatant layer and the scum layer. Okay, so the acid is formed here, and that acid is taken to the second stage where you have the here there is no mixing happening, so you still have the supernatant and the scum layer. Okay, and the methanogenesis takes place in that is the phase 3 of the final phase of the final stage of the entire process takes place over here, and the gas is taken from the top. So this
Sir,
is yeah.
so the scum layer and the supernatant layer are
Mhm.
not to be present, so they are to be removed.
Supernatant layer is still okay, but the thing is, it just indicates that it's not properly mixed. And what
Mhm.
happens? You may lose lose some organic matter in the supernatant layer. The scum layer is more like
Waste,
whatever
waste.
is non-digested, whatever is not digested, it just floats on top. So if you take straws for example, okay, and if you mix water with let's say rice straw, you might have seen it. I mean,
It's
before feeding
floating.
to
Yeah.
animals, yeah, before
Yes.
feeding to animals, they mix it with water, right? So what
Yes.
happens? You have that white kind of fluid, the starchy fluid, that starchy liquid that is fed to the animals. But there are some the stock is floating on top because it is
Yes.
very light. It is still floating on top, and that is one
Yes.
issue with using agricultural residues, especially stalks and all, for biodigestion.
Mhm.
Okay. So that
Yes.
floating, that organic matter that floats on top is the scum layer. Okay.
Okay. Yes, sir.
So this kind of like, because it's forming layers instead of mixing all together, it inhibits the methanogenesis or the entire process.
Mhm. Okay.
So these are some biodigesters. So this is KVIC floating drum type biodigester. So so you can see the digester itself is fixed. So it is made of masonry, and then it's below the ground level. Okay, but there is a drum that is floating on top. Okay, you have the mixing pit here. So this is where you mix the the organic material, whatever you have, with water, and then so it goes down from here. The digestion takes place within this chamber, so it moves from here. As and when we add more, so there's no pump or anything required. It's just through pressure. So this moves up, and then it moves to the next chamber. So this is a partition wall, right? So the here the function of the partition wall is to, you can also call it a second two-stage kind of, but we are not actually actively separating out the acid layer or anything. Okay, this just, it could happen that way, that the acid is formed here and then the acid moves over here and the digestion is taking place, but that's not exactly we are not doing it actively, right? Then the sludge is formed here. I mean, the digested sludge that moves to the top. As and when you add new material, it gets just through pressure, it just moves to the top here. And the gas is formed. The gas gets formed and it goes to this drum, and the drum moves upwards. So you can see water here. So this is the water seal, right? So water is until here so that the gas does not escape through the water into the atmosphere. It goes just into the, I mean, it should not leak through the sides, right? So you have a water seal on both sides, or I mean, on all sides, and then the gas is collected here. Okay. Why do you think we don't require any kind of external energy to move this around? I mean, to move the fluid and move the entire materials around. Can you tell me that? Just look at this diagram and you can tell me.
So the constant motion of gas steers it around.
It's not about the gas. Okay. See, basically, the organic material is fed from here, right? So as and when more material is fed, it just goes to the next partition. The gas is formed. That's okay. Gas goes up. That is normal. But then even the sludge, which is liquid, it goes through this pipe and it gets collected here. Why is that?
So is it because of the pressure of the gas?
It has nothing to do with the pressure of the gas. The pressure of the gas is exerted over here. The gas rises up to the top and the pressure is exerted here. This moves up. This drum moves up as the pressure is increasing.
Sir, are you using a pointer or something?
Using what?
Pointer or something?
Yeah, the red one. Can you see it?
Because
It's
we
not
can't see the
visible.
pointer actually. So,
Oh,
Yeah, it's not visible.
can you see this?
Yeah,
now
right
we
now.
can see.
Yeah.
Yeah, okay. So I'm saying the gas is formed over here. The gas moves to the top. The pressure of the gas makes this drum to move up. Okay. So what happens to the liquid, the semi-solid or whatever that the mixture, right? How does the mixture move up here? Or rather, why does it do that? I mean,
Because
you
it does
look
not
at
have
this
any other
picture and
place to
then,
go.
sorry?
Because the gas holder is it won't come off, so it has a limit. So the liquid does not have any place to go. It's like
Yeah, but then, I mean, it's moving from down to up on its own. Doesn't that
it's like
violate the laws of thermodynamics?
it's
So
like
is
if
it
you have
is there
a
some kind of suction force, sir? Like the atmospheric pressure is
There's
lower
no, I
on
mean,
lower.
it's close to the atmosphere, right? So where is the atmospheric
Yeah.
pressure here?
Okay.
it's like
Or
if you
even if
have
you
a
consider that this is open and this is open, both are at the same pressure level, right? I mean, both are at the atmospheric pressure. Due to pressure gradient, where? Where is the pressure gradient?
between the like the below the thing underground and the outlet and that thing.
Okay,
The
I'll
only
give you an
difference.
example. I'll give you a hint. Uh, have you heard of this term? Have you had fluid dynamics, fluid mechanics course already? Anyone? Fluid mechanics?
Not yet.
Not yet. Okay. There's something called capillary movement. Not exactly capillary movement. Okay. I'll tell you. There's something called pressure head. Have you heard of this term? Pressure head or just head?
No, sir.
No. Okay. So what is the head? What does that mean? So if you see so let's say that there is a waterfall. Okay. So that has a very high, I mean, it's quite high, right? So you keep a turbine at the base of the water falls on it, and then it kind of moves around, right? So what is the potential energy of water at the top of the waterfall?
The weight of the thing multiplied by the height at which it's there.
Weight, height,
Of the
yes.
water, yeah, of the water.
One more thing, what if the energy rho gh? Yes, exactly.
Okay.
Rho gh, yeah. So rho gh is so what is that h in that rho gh formula? Rho gh, or some people say mgh. That's okay. Yeah. What is that h
Actually,
there?
height above the datum, sir.
Yeah, that is the head, pressure head. So, and it's not exactly the head. It's not the exact height of the waterfall. It's the relative difference between the heights. Okay. So if you have the turbine at base level, then you have 0 to whatever height it is. If you say, no, I don't want it at 0 level, I want it at somewhere in between. Let's say I'll go to half its height. Then your head becomes h minus half h. So it is 0.5 of the total h. So that is head. So basically what happens is if you have something at a higher level and something at the lower level, it doesn't matter what happens in between. The fluid will flow between the higher and lower level. So it doesn't matter what happens here. Okay, here it is obvious. It is moving down. But here it's moving up. Here it's moving up. How is it doing so? That's because the height over here is higher. I mean, this is higher than this thing. So uh, naturally, it should move from here to here. It doesn't matter what path it follows, as long as it comes back here. So even if you take this to a much higher place and then bring it down here, that should also work. But then if this is over here, then it won't work because now you're trying to move it from this height to this height without adding any additional energy. You got the point? So it's just moving through gravity. That's it. Gravity
Yes,
and displacement. So here it's gravity, and then it's moving here through displacement by adding new material. Here again it's gravity, and again through displacement. That's it. But if you place this tank over here, there cannot be any displacement from this level. I mean, from this level till here, because you are trying to move it from a lower potential energy to a higher potential energy, and that is not possible without adding any new any energy. So you need to use a pump or whatever it is. Okay. Okay. Yeah.
So the partition wall, what is mentioned here, is it like a solid wall which doesn't uh, let anything pass through it?
Yeah, it's like a solid wall.
Okay, okay, okay. So whatever the material is, it has to go up and
Yes.
down on the other side. Okay,
Yes.
okay, sir.
This might also be done because I mean, naturally the gas has to move up, but just to aid in it, so that the
Yes, sir.
gas automatically moves up. And
Yes.
also as a partition between the two stages, just making it
Oh,
naturally instead of making a two stage like we saw in the previous
like
slide.
separate digesters for
Yes,
acid and
yes, yes.
biogas.
Phases 2 and 3, we just separate
Yes,
it,
sir.
and yeah. Okay. So next is this is also another floating type digester. You can see there's another partition wall here. Okay. Uh, this is very similar to the previous one, just that it has a higher volume over here and a little lower depth. Okay, so this is suitable, this one and a few others, I'll tell you maybe in the next couple of slides, suitable for higher altitudes and places where you have a high water table. So if you have a high water table, let's say you get water at 4 feet, 5 feet, then you can't really dig deep, right? And you can't have this kind of a structure below the ground. Okay. So in this case, what happens in the previous case, like the depth is too much. So you can't really go very deep. So instead you increase the volume, and then the depth automatically reduces. You maintain the, so increase the width basically and reduce the depth, maintaining the volume. Okay. And here also you can see the head difference between the inlet and the outlet. And you have the gas storage, the drum, right? So it's the same concept here also. Next is the fixed dome type Janta biogas plant, where you have the inlet and the outlet. So this is almost at the same level, but yeah, there is a slight head difference here also. Okay. So the digestion happens in a single tank. Okay. And the gas rises to this, I mean, the top half of this tank, right? Top half of the biodigesters, it's stored over here. And whenever required, the gas is emptied out. So this is completely below the surface of the earth. Okay, it's not there's no floating, so you can only see a pipe here. So you can just use it whenever you require. You can connect it to some machine or whatever it is directly. Or if you want to connect it to a, I mean, if you're going to transport it, let's say a compressor or something, and then you can fill a tank and then transport it to some other place. Yeah, so this one, okay, why do we do this tapering? Can you, so this is a taper biogas digester. This is a with a floating drum. So tapering is like steps over here, right? So it's the width is just increasing as the depth increases. Why do we do this? Any idea? It's very similar to the Pragati plant that I just told you about over here, right? Very similar to that.
To increase the volume.
Yes, to increase the Not the volume itself, because like I said, it's the same. If the water table is high, or if you're going to higher altitudes where you have to install this, then you can't
Yes.
really dig deep, right? You can't dig
Yeah.
very deep. Mountainous terrains, for example. So you just have to make do with whatever depth you can go to. So if you have this kind of a design where the width is just increasing, the depth can be reduced in that case. Okay. There's one more reason I can think of is where if the width is increasing, as you go down, the pressure is lower. So as you remember, the pressure, as close it is to atmospheric pressure, it is better for the conversion. Okay. So at this level, the pressure will be high because of all the the slurry on top of it. So you can reduce the pressure using this. But I mean, that is true of fluid flow. Here there is no flow as such. But yeah, main reason is to reduce the depth of the biodigester. So this is another fixed dome digester, but there is a separate gas holder here. So this is kind of like a mix between the two. So you have a fixed digester here. The gas is stored over here, but from here there is another gas holder where you have a water seal, and it kind of rises to this drum over here. This is a movable drum. Okay. And you can store it here. So you have like two kinds of storage here. One is the fixed storage where here the pressure is high. So if the pressure increases too much, you can displace some of this. You can move some of this to this holder. And then this moves up as the pressure increases over here. So some design considerations of biogas digester. So you have to consider the volume of the digester, volume of the waste to be digested, the type and amount, the retention time, what are the stirring methods, the climatic conditions, because the temperature plays a very big part in the reaction moving forward, right? So if the temperature is between 25 and 35, that is ideal. But during summers, it may go up to 40 or even more, right? So that time it could be an issue. And in some regions in India, in winter, it may go to below 20, below maybe even 15, 10. So, I mean, even less than 10 also. So that is also an issue. Then also the reaction won't move forward. We need to make sure that the digester is maintained at a certain temperature. Okay. And water table and soil conditions, like I said, because of high water table, if the water table is very high, we have to ensure that the depth is not too much. So we increase the width so we can maintain the volume, but reduce the depth. So how do you calculate the volume of biogas? So that is calculated using the mass of the dry input to the digester times the biogas produced per unit dry material. So that is around 0.2 to zero point 0.4 cubic meter per kg. So if you put like, let's say 1 kg of biomass, maybe cow dung or agro residues, whatever it is, around 0.2 to zero point 0.4 cubic meter of biogas is produced. So using that times how much biomass have you put in? So that gives you the volume of biogas. Uh, the fluid volume in the digester is given by the so this is a straightforward formula. So you have volume equals mass by density. So density equals mass by volume. From that you get this. So this is mass and density of the dry material. So that is the volume of the volume of fluid in the digester. Okay. So using this, the volume of the digester can be calculated. Okay. How can you do that? So you have the fluid volume times the retention time. So that is the volume of the digester. So retention time may be about 40 days, 50 days, whatever it is. So calculate the fluid volume in the digester times the retention time. Okay, you'll get the total volume of the digester. So that's the end of biogas biomethanation. If you have any doubts, you may ask me. Anything?
No, sir.
Okay. So let's move on to second generation bioethanol. We spoke about this in brief in a few of the previous lectures. Okay. So a recap of the agricultural residues and the biofuels. So there are three generations of biofuels. The first generation, where ethanol is produced from crops and grains such as rice, maize, wheat, etc., from the grain itself. Okay. So the controversy here is that using this kind of food crops, right? Food crops for ethanol generation could be detrimental, and that was a debate. I mean, it's an ongoing debate since the last 50 years. It's been going on. So since there was an oil crisis in the 1970s, and that was the first time anyone thought of ethanol as an automotive fuel. It started first in the US and then in Brazil, but then quickly they had to, they had this debate because they were using maize for production of ethanol where people were going hungry. Okay. And even recently, with respect to the bioethanol policy, so we have produced, I think, yeah, we are at 10% ethanol blending as of 2022. We may be at 12-13% right now. So our target is 20% by 2025 next year. Okay. But recently, about 6 months back, it so happened that there was no sugarcane left for the sugar mills, so the sugar prices were going up. So the government said that okay, and now we'll focus on the sugar prices, on the sugar production from sugarcane, so that the prices go down, and then we'll come back to ethanol when the prices are stable. But it's kind of like a monkey balancing that is happening, and that is why it is controversial. 2G ethanol, the issue with 2G ethanol is, okay, 2G ethanol is produced from lignocellulosic biomass like straws, agro residues, and so on. There is very little sugar content in that, so you have to make it available to the microorganisms for their fermentation to take place. So you have to do some pre-treatment to break the lignin first. Then you have to do some hydrolysis to break the cellulose and hemicellulose, and then uh, uh, to make it available for fermentation. So it is very expensive. 3G is still in a research phase, which is produced ethanol produced from algae. So the agricultural residues, there are two types. One is primary and the other is secondary. Primary is where the residues that you obtain on the field directly. Like once you harvest, let's say rice or wheat, and then you thresh it, you get the straws right there on the field. Whereas a rice husk, when it's separated from the bran, right? It's just the outer covering, right? So it's separated from the bran in the industry, in the rice mill. Similarly, you have sugarcane. Sugarcane, you have the leaves and tops and trash and all that lay on the field. You can collect that. So that is primary biomass. But then the bagasse, what is bagasse? You remove the juice, and then what is remaining is bagasse. Okay, that you can get only after processing in an industry, in sugar mills. Okay. And we know about, so what are advanced biofuels? Advanced biofuels are anything but the first generation. So second generation, third generation, they are all advanced biofuels. Okay, so basically whatever you produce from biomass, or lignocellulosic biomass like agro residues, or it may be even wood or anything, that is not that is not food, that is not used for food. That's basically it. And there are different production pathways. We've already seen that. So you have biochemical and thermochemical conversion. So coming to the crop yield and crop to residue ratio, there are a few crops, or rather there are a few residues from which ethanol can be produced. And these are, corn stover. What is corn stover? So you have the plant that is standing. So you remove the corn from the plant. Okay, so have you seen the corn fields? The corn is like hanging from the plant, right? So once you harvest the corn, whatever is standing there, that is the corn stover. That is including the leaves and the stem and everything. Okay, that is corn stover. Okay. Switchgrass, it's a type of grass that is grown directly, so it's only for energy purpose. Okay, it's just a grass actually, but then it has very good properties. It can be converted into ethanol. It can be fermented into ethanol. You can use it to produce biodiesel. Okay, so this is very famous in the USA. Okay, but growing them in India, I don't know about the climatic conditions, but socially it might not be very acceptable because again it will lead to a food versus fuel debate. Because are you using the land? Now we were talking about using the crop itself for food or ethanol. Here it's more about what you use the land for, to produce food or to produce fuel. That's the question here. Okay. Then you have sugarcane bagasse, rice straw, and rice husk. So sugarcane is produced mostly in Brazil and India. Rice is produced in China and India. And let me just turn your attention to these two numbers over here. Something that we need to desperately solve in our country. You can see that the crop yield of rice, it's up to 10 tons. The maximum is like 10 tons per hectare in China, whereas for us it's 2.5 tons. Okay, so China is like 4 times ahead of us. Okay, so something that I mean, it can't be that they have much more fertile lands or something. Even if they did, it cannot be 4 times. The difference cannot be 4 times. Okay, so what is crop to residue ratio? So if you have, let's say rice, you take rice for example, the rice grain that you have, what is the weight of that grain divided by the weight of the residue, that is rice straw or rice husk. So if you see here, it's 0.41 to 1. That means for each kg of rice, you have 0.41 to 1 kg of rice straw and 0.2 to 0.33 kg of rice husk. Similarly, you have for corn stover, switchgrass, and sugarcane bagasse. So what is the process for producing ethanol from uh, through fermentation? So you have the agro residues. You do the pre-treatment and hydrolysis. So in the pre-treatment, you remove the lignin from the biomass. So you separate out the lignin. Okay. The lignin is a byproduct. It's again combustible. It can be used in a CHP plant that produces heat and power for use in this plant itself. Okay. And the remaining cellulose and hemicellulose, first it has to go through hydrolysis. Okay, where decrystallization of the cellulose, hemicellulose that happens, and then the monomers are released, the sugars are released, leads to fermentation, and fermentation leads to ethanol. So a little more in depth. So you can see here the biomass. The pre-treatment releases lignin that is separate, but it releases C5 sugars. The hydrolysis releases C6 sugars that can be fermented to form bioethanol. Okay, so as you know, the lignin kind of forms a protective covering. Okay, so this needs to be broken first before the hydrolysis can happen. So pre-treatment is done to depolymerize the lignin and obtain access to the cellulose and hemicellulose. And the cellulose and hemicellulose are polymers. Okay, so they need to be hydrolyzed to obtain fermentable sugars. And if you look at the pre-treatment process, what must it achieve? First is preserve and decrystallize cellulose. So it should preserve. So there are acid pre-treatments that are available, but what happens is because of the strength of the acid, it destroys a part of the cellulose and hemicellulose also. A perfectly good cellulose and hemicellulose that can otherwise be used for fermentation is also destroyed in the process. So that should be avoided. Okay. So decrystallize cellulose and depolymerize the hemicellulose. Okay, and restrict the formation of inhibitors. So what are inhibitors? So you have because you're using some chemicals for the pretreatment, and those chemicals might be harmful for the bacteria that are doing the hydrolysis. Okay, so if there are chemicals that are detrimental to the bacteria performing the hydrolysis, they inhibit the bacteria. So they are called inhibitors. Okay, it has to have low energy input, of course, and then it should also allow for easy recovery of lignin. So because lignin is a value-added product that can be used in a power plant to produce electricity, that can be a byproduct, or it can be used within the process itself, within the premises, let's say the lab or the plant itself, wherever required.
Sir, what is a CHP plant, sir?
Combined heat and power.
Okay, sir.
Okay. So here I have a couple of links actually. I don't know. I don't think you can see this, but what I'll do is I'll share my desktop instead of just sharing the presentation so you can see. But before that, we'll just go to this one. So land footprint of 2G ethanol to produce 1 million liters. It's from the same study of that crop to residue ratio and all. So you have the the corn stover from US, rice straw from India and China, bagasse from India and Brazil, and then switchgrass from the US, right? So you have to produce 1 million liters of ethanol. You need how much? How much land in hectares? Okay, so let's say to produce 1 million liters per year. Okay, how many hectares you need? So in US, using stover, you need like 350 hectares. In India, if you use rice straw, India versus China, you can see the difference here. You need 300 hectares of land in India, whereas you need about what 50, 70, 75, right? So it's exactly 1:4. The same ratio of the yield of the crop, right? It's in the same ratio, right? So you need 300 hectares to produce 300 hectares of rice straw to produce 1 million liters of ethanol, whereas you need only 75 hectares in China. And similarly, bagasse, it's very similar. Actually, in fact, yeah, it's almost 50-50 between India and Brazil. But then India is slightly higher. Okay, that's still okay. And you have the switchgrass, which has the lowest lowest land requirement of any of the four crops, right? It's about 150 hectares. Oh, but then this is also lower, right? I mean, yeah. So this is about, I think, 120 hectares. This is another 100 hectares. Okay, less than 100 hectares. Okay.
Sir,
Yeah.
about bagasse,
Mhm.
what I have seen is a lot of bagasse is just dumped, and that it has become a problem in recent
Where
years.
where is bagasse dumped actually?
Like after the sugar is produced, the rest, the waste, whatever, yeah, the bagasse only, it is
So
dumped. It seems. I don't know exactly where.
actually, as per statistics, what we have, we don't have any excess bagasse left at all, any surplus
Oh,
bagasse, because the sugar mills, what they do is this is not a waste product for them at all. There may be a few sugar mills here and there that is not using it. Okay, but most of them, what they do is they don't want to purchase electricity from outside, so they use this
okay, so they
bagasse
use
to,
the bagasse as a
yeah,
fuel for
yes,
their.
as a fuel for
Okay.
they use it in a CHP plant. Like they produce heat and power, both of which they require in their plant.
Okay.
Okay, that's what usually
Yes, sir.
happens. But
Yes.
it may be possible that in some places you may have seen that. Okay, but mostly that's not a waste for them at all. It's like literally it's a fuel for them. Okay.
Okay, sir. Yes, sir.
So before I stop, let me wait. I will share the screen. So you can see this, right?
Yes, sir.
Sir.
Right, and just close everything else. Okay. So you can see this. So the different types of treatment. Okay. The pre-treatment processes. So you have acid treatment, you have alkaline treatment, you have ammonia treatment. All of these are different types of pre-treatment. And then you have organosolvent, organic solvent, and all that. Okay. Oxidative delignification and all. So acid treatment is, the advantages and disadvantages are given here. So increase in porosity. Why does this happen? Because it kind of dents the material because the acid is very strong. Okay. And but that leads to, because of the porosity, right? Because of the porosity, it leads to increased enzymatic hydrolysis. But then the disadvantage is that it generates inhibitors like furfural and furfural basically, and it needs to be recycled. It is costly. And similarly, you have, and like I said, the inhibitors, and it may also lead to. So you can see the yield here. It's very low compared to the other types of pre-treatments. Okay, and that is because it kind of destroys a part of perfectly good cellulose and hemicellulose that can be used for the fermenting process, right?
And
And
does it affect the bacteria also?
yeah, that's what this formation of furfural is. It's an inhibitor. Okay, similar
Okay.
to this one, formation of salts of calcium and magnesium. So all of that, all of those are inhibitors, which affects the hydrolysis process that comes after this.
Okay. Okay, sir.
Okay. Similarly, you have alkaline treatment. The advantage here is removal of lignin, so it aids in the removal of lignin. But then it goes into, I mean, there are some inhibitors here also. But you have a yield of 93.1% glucose and xylose that is yielded here, and 60% here, 58.2. So depending on what the biomass is and what the treatment is, like calcium hydroxide, sodium hydroxide, potassium hydroxide, and so on, right? And you have ammonia treatment, and you have liquid ammonia at high temperature and pressure, all of these. Okay. So you can just go through it. I'll send you this second. And the second one is the difference between first and second generation ethanol. So it's just what I have already told you. So they are produced from types of biomass that are often used for food, whereas this is non-food biomass like perennial grass. So switchgrass is a perennial grass that is grown on land for energy basis. Fast-growing trees. Again, you can have a plantation. You can have like land where you can grow these trees. Maybe in 2-3 years they'll mature, and then you can cut them, and then you can grow them again. So in a sustainable manner, you can do that. Okay. So these are the differences. So you can see the rise of the first generation. I was just telling you about the oil crisis, and how in in the 1970s and 80s, the ethanol kind of, just shot up. So from the 1990s, 80s, you can see that it has shot up. But after 2000, so until the 1990s, it was more of, okay, what happens if there is no oil or there's no crude oil supply from the Middle East. Okay. after the 1990s or during the 1990s, there came this, new study on the climate change and everything. So now after 2000, the kind of exponential growth that you see here, it's because of that, because of the environmental concerns. Okay, so it's still dominated by ethanol in the US, and a little bit of biofuel, biodiesel has been produced since the 2000s, right? So the food versus fuel I was just telling you about, so you can have a look at this also. So this is the perennial grass. So this is switchgrass, right? So the benefits and barriers of second generation biofuels. So here, the main drawback here is that the markets and technology are not well established. So we were just talking about this, right? So, so basically, what happens is, so the second generation biofuels, if you are taking residues from somewhere, where will you use it? Okay, the technology is not very widespread as of now. You can only use it to produce second generation ethanol through fermentation, which is very expensive. And you can go for thermochemical conversion, but that is also not very commercial yet. Okay, but that is a very good alternative to second generation ethanol. But you cannot produce ethanol so efficiently in that using thermochemical conversion. What you can do is you can produce maybe hydrogen or methanol or maybe some other biofuels, but ethanol is not very possible. It is possible, but then the efficiency is very low. And that is the major drawback of second generation bioenergy crops, right? And that's why it's not very well established. So you can have like, let's say all these perennial grasses can be used to produce biodiesel, or even there is something called sustainable aviation fuel. Okay, you can use the grasses directly to produce that. And in fact, and there is a group in Dehradun that has come up with a biodiesel using, used cooking oil is one thing, using these perennial grasses and used cooking oil. And there was a spice jet airplane that was run like in one of the engines was run using, I think, a 25% blend of sustainable aviation fuel with the normal one. So they tried that and it was a success, but then scaling it up to to produce it in a commercial a commercial stage, that is the issue here. And if that happens, then we can all go for this kind of plantation, provided it doesn't compete with food and everything. So you have third, there's something called fourth generation also. Okay, so what is fourth generation? So biofuels that capture and sequester carbon dioxide. Okay, so third generation is algae or engineered biofuel crops. Fourth generation is this, but it is still, it requires additional research. Okay, so I'll send you both of this. You can have a look. Okay. Right. So let's go on to the questions now. Okay. So you can read this question. 10 kg of cow dung is mixed with water in 1:1 ratio to provide a total solid content of 8 to 10%. Okay, so cow dung, the wet cow dung itself has 20% solid content. So if you mix it in 1:1 ratio with water, it goes to 10%, like 8 to 10% of solid content. So the biogas output of the digester is around 2.4 cubic meter per day after a retention time of 20 days. So if the density of the dry biomass is 50 kilogram per cubic meter, what is the fluid volume in the digester? What is the digester volume itself? And if the gas is emptied out once in every 6 years, what should be the volume of the gas holder? You tell me the steps to do this, and then I've given you the formula. How to do this, right?
So the fluid volume in the digester is given by
Mm-hmm.
Vf equal to m by rho,
Yeah.
where mass by the density of the dry material.
Yes. It's the mass of the dry material itself, not the total mass. Or, oh, sorry, it should be the total mass actually, not the mass of the dry material, but yeah, go ahead. Mass of the mass of total mass by the density of the dry material.
Density of the dry material, yes.
Yeah, density of the dry material. So how much is that?
Okay. Mass. So the total total mass is 10 kg plus 10 kg water, so 20 kg.
Oh, wait. Okay, yeah, true.
20 kg, and the density is given 50 kg per meter cube.
Okay.
So 20 by 20 kg by 50 kg per meter cube.
Yeah.
Which will give us the value 2 by 5, 0.4 meter cube.
Yes. That's right. What is the digester volume?
Digester volume is the fluid volume into retention time.
Yeah.
So 0.4 meter cube into 20 days. So 20 should it be in seconds or
No, it is
like
days only. It is
days
days.
only? Okay.
Days.
So 0.4 into 20.
Yeah.
8 meter cube.
Yeah, that is true. So the next one?
Next one is if the gas is emptied out once every 6 hours, what should be the volume of the gas holder?
Yeah. We calculate how much biogas is produced in 1 day.
1 day, the biogas produced in 1 day. So the volume of biogas produced is given by mass mass of the dry input into the C. What is C here? C is the biogas produced.
I've not given it. You can assume. The
So
biogas
what is the
produced
mass
per
of dry input, meaning the whatever mixture is put into the plant, put into the digester. So it is 20 kg. And C is the biogas produced per unit dry material.
Yes.
So in the slide, you have mentioned it as 0.2 to 0.4.
Yes, meter cube per kg.
Per kg. Yes.
Yeah.
So 20 kg into, should we take it as
So
0.4?
wait, no, you don't have to do it that way. I think let's do it this way. So you know the digester volume, right? In 20 days, it's producing what? 8 cubic
8 meter
meters.
cube. Yes.
So I think that's it. So that can be the I mean that can be your production in a day or something. Okay.
0.4
So
meter cube is the
so
fluid
even
volume.
if you consider 0.4 meter cube, you'll still get 8 only, 8 meter cube.
Okay.
Right.
Okay.
So if that is per day, then how much should it be in what, 6 hours?
6 hours. So we have to divide it by 6. No. Multiply it by 24 and divide by 6.
Yeah.
Just a minute. No.
Are you sure?
No. So 8 in 1 or 24 hours. So how much in 6 hours? So 8 into 6 by 24.
Yeah. What is that?
2 meter cube.
So what is the digester volume? What is the gas holder volume?
So gas holder volume.
Yeah.
2 meter cube.
Yes. And the digester volume is?
Digester volume is 8 meter cube.
Yeah, that's it.
Okay, sir. So
Okay.
the gas holder volume is 2 meter cube, and the digester volume is 8 meter cube. Okay, yes.
Yeah. Okay.
Yes.
So you need to build
Yes.
a digester that can hold 8. I mean, the digesting itself is 8 cubic meter because of the fluid volume in the digester. And then the
Okay.
gas on top, it's like since you are emptying out every 6 hours, you need storage only for those 6 hours, which is 2 meter cube. That's it.
Yeah. Okay.
Okay. So after 20 days, you will have continuous flow of gas. The first 20 days, you won't have any gas. That's how it is,
So
right?
you will let
Because
it
it's a
to
slow
get
process.
pressurized.
No. I mean, for the digestion to take place initially.
Uh-huh.
Okay. So then you keep on adding new material, and then every day you'll keep getting the same output.
Okay. Sir, just a
Okay.
minute. Can you show the questions?
Yeah.
Here you mentioned the biogas output of the digester is around 2.4 meter cube.
Oh, wait. I have already
The
done that.
amount of
Oh, sorry.
biogas produced.
Yeah. So then you can use this only directly.
Right, it's mentioned that it's 2.4. So
2.4 meter cube per day, but the digester volume will remain the same. That is 8 cubic meter. That will be the same. Okay. Then
sir.
this one will be 2.4 cubic meter per day, right? So this will be into 6
2.4
by
into 6
24.
by 24, yeah.
Yeah. So that will be around what, 0.6? Yeah, 0.6 meter cube.
Yes, 0.6 meter cube.
Yeah, so that's it.
Yes, sir.
Okay.
Yes.
Next one is, what is the difference between first generation and second generation ethanol? List two advantages and of 1G ethanol over 2G. Disadvantages. So differences we have already spoken about. I'll just ask you the disadvantages.
Disadvantage is the debate on food versus fuel.
Yeah, that is one. One more disadvantage I need here.
One more disadvantage is the land required.
That is again,
Is
I mean, it's a debate again on this thing, right? Food
based on
versus
the type
fuel.
of okay.
Yeah.
Okay.
So let me tell you. So in 1G ethanol, what happens is you are using the grain directly, which is the main product, to produce ethanol. Okay. So let's say you are using rice to produce ethanol. In that case, what happens is that whatever, so I told you about paddy cultivation, right? Before this.
Yes.
So what happens during paddy cultivation?
Like there is a water barrier which will separate the atmosphere from the surface below.
Yes.
And there will be methane formation there.
Yes. So methane emission is there, which is greenhouse gas.
Yes.
Now if you consider 2G ethanol from paddy. So 2G ethanol is you're using the byproduct of agriculture, which is a rice straw or rice husk. Okay. Then what happens? The impact of this environmental emission, right? The methane emission, it gets divided among the two. Okay. There is an allocation of the impact to the, to the main product and to the byproduct. So the allocation is very low to the rice straw because the allocation can be done in two or three ways. In fact, it can be done in the through mass, energy, or economic value. Okay. The most logical way to allocate the impacts in this case is economic value. So let's say you sell the rice or sell the paddy for 20 rupees, and you sell the rice straw for what, 1 rupee per kg. So the ratio becomes 1/21, right? Only that much impact is allocated to the rice straw. So if you have 100 tons of carbon emissions, only 1 by 21 of that is allocated to the rice straw, and the remaining 20 by 21 is allocated to the rice itself. You get the point?
Okay, so the rice,
Yeah.
so if we use rice as like the 1G for ethanol production, it has already given its contribution to the global warming, like through
Yes,
production of
it has.
methane
It has.
when it grows.
Yes. So
So it will
100%
have
of that
another.
impact,
Yeah.
100% of the impact comes to the ethanol. So you're not exactly
Yes.
sure if it is green anymore,
Yes.
right?
Okay.
Because you cannot call it green if you're, especially if you're using rice and you're emitting so much of methane, and then you're using it directly to produce ethanol, and then you call it as renewable or green or reducing. In fact, you're increasing global warming by doing that.
Yes.
Because there is so much emission of methane and even nitrous oxide because of the fertilizers that you cannot actually escape from that. On the other hand, if you use just the rice straw, the impact that is generated during the the growth phase of the paddy is allocated between the two. Only one fraction of it comes to the rice straw or the rice husk. Okay, this is true of any biomass, any residue, agro residue that you use. Okay, so and that is another disadvantage. There's something called land use change. So if you're clearing out forest to make agricultural lands, then the stored carbon, the forest would have stored some carbon in the soil. Okay, over the years. So all the
Yes.
stored carbon in the absence of the trees get emitted to the
Released
atmosphere.
back into the atmosphere.
Yes.
Which will
So
again
that
increase the
that is a
atmospheric.
huge deal. Okay.
Yes.
So any questions until now? I think that's it for today. I'll just stop sharing now.